Hi, I'm Ben-Yaakov. This presentation is entitled Answer to Power Electronics Riddle, Current Direction. This is a answer to a riddle that I've posted earlier, so I'm going over it very quickly just to see what were the questions, and then I'll give my answer to it. So I'm showing here two converters. One is the buck, one is the boost. On the surface, they look the same half bridge here. This is a synchronous boost, and this is a synchronous buck, of course. And they look sort of the same. And I've labeled here the timing of the gates as T1 and T2, and also here T1 and T2. This is to add a little bit to the confusion, because the duty cycle of the buck is usually related to this transistor. This will be T on, while for the boost, this timing will be called T on for the duty cycle. So I've just labeled it this way, and I'm giving this information about the timing, about the actual duration, 3 microseconds for T1 and 7 microseconds for T2, and I'm assuming that they are running at continuous current mode. The questions are related, first of all, for the voltage transfer ratio between the input and the output, given these timings, here and here. This is now the input, this is the output. And more importantly, what determines the direction of the current? Because on the surface, everything sort of looks the same. You have a half bridge here, you have a half bridge here, you have a voltage here, you have a voltage here too, of course, at steady state. And then you have a voltage here and here. At steady state, there are DC voltages there. And yet, in this case, the current goes this direction. And in what we call the buck, the current goes in this direction. So the question is, what is determining, or what is the process, or how can you explain in an intuitive way the direction of the current? So here are the specific questions. What are the voltages? And at steady state, what determines the direction of the current flow? So let me start off with the duty cycle, or with the transfer function, voltage transfer function, which is kind of obvious, because in this case of the buck, we called T1 as T on. So therefore, the duty cycle is T1 over T1 plus T2, here it is, 0.3, and since we have a 10 volt, then the output is D on times V in, which is 3 volt. Now in this case, which is kind of tricky question, the T on is actually T2, but the transfer function of the boost is V in over D off, and now D off will be T1 over T1 plus T2. So therefore, V out, which is V in over D off, is 1 over 0.3, which is 33 volts. So this is really trivial. It's just a matter of confusion here. What is T on and what is T off? And now what about the direction? There are many ways to look at it, and I'm actually looking for an intuitive explanation, not how the current is pulsating and how it's injected at the output, but something that is kind of basic. And the basic thing is that the current flows from a source to a load. That's it. So what I'm going to show is that you can sort of describe each of these converters as an equivalent source and an equivalent load. And then the direction of the current is kind of obvious. So for the buck, it's trivial, because we have here a average voltage, which is V in times the duty cycle. So this is like a dependent voltage source. For DC, you can sort of eliminate the inductor, it doesn't add anything. So basically, we have a source here. We have the output section. At DC, we have just a resistor. So obviously, the current goes this way. So for the buck, it's really trivial. However, the riddle is really more directed to the boost. Now, what about the boost? This is the tricky one. Now, the way I'm going to treat it again is the same way as the buck, That is to sort of convert it to an equivalent circuit in which we have a source and an equivalent resistance. Now, in this case, the equivalent resistance is the resistance that is seen here. Okay, this is the source, and this is the equivalent resistance. And I'm going to calculate this equivalent resistance as the ratio between the voltage and the current here. So I'm assuming a certain current here, IL. If I have this current, then the output current is a function of it, and the output voltage is the output current times the resistance of the load. Now, the output current is the inductor current times this ratio, because the high side transistor is turned on at T1. So the average current coming here is T1 over T1 plus T2 times IL. And then I can plug in, instead of the output voltage being the output current times RL, I can express V out as a function of the inductor current, okay, by this. And then the midpoint is also a function of the output current, because the high side is turned on during T1, so the average voltage seen here when looking into this midpoint is V out times T1 over T1 plus T2. This is the voltage at the midpoint. Now the equivalent resistance is the voltage times the inductor, and as you can see, the output voltage drops out because we are expressing it as a function of the input current, and therefore we find that this resistance is equal to the original resistance of the load, RL, times this factor. This makes sense because the input voltage is low, the output voltage is high. So for the same power, the equivalent resistance here has to be lower than the real load RL. So now we have R equivalent, and therefore this is the simplified DC condition that we have at the input, a source plus an equivalent resistance, and clearly the current goes this way. Okay, so this is the real current, this is the direction of the current. So this brings me to the end of this presentation. I hope that it sort of helped you to look at an intuitive way, or an additional intuitive way, to these two converters. Thank you very much for your attention.